Introduce the next plenary speaker, my colleague and friend Jorge Vitório Pereira from IMPA. His work lies at the crossroads of foliation theory and algebraic geometry, with a special emphasis on holomorphic foliations, on complex manifolds, and the birational geometry of foliations. Jorge's many works, especially about transcendental leaves and vibration divisors, have shaped the modern understanding of foliations in algebraic geometry. In addition to his scientific work, he is IMPA's vice director, and he also coordinates the Brazilian Mathematical Olympiad, which has the participation of over 20 million students every year. He will be an invited speaker at the next International Congress of Mathematicians in Philadelphia in 2026. Today, Jorge is speaking on foliations with trivial canonical class. Please.
Thank you. Thank you, Marcelo. It's a pleasure and great honor to speak here at the MCA. I'll start by thanking the organizer for the invitation and the opportunity to share some mathematics with you. And as Marcelo told, I will talk about foliations with trivial canonical class, but we will start by introducing the main object, the main character of the talk, which are the foliations. So foliations are the composition of ambient spaces in disjoint subvarieties of the same dimension. They can be studied in different settings, continuous, differentiable, analytic, holomorphic. And they are usually, they can be defined by local submersions, level sets of submersions. It's a reasonably recent theory created in the decade of 1940 by George Hebb, a student of Charles Erisman. And he did that. One of his original goals was to provide a proper framework to understand Plenary work on second-order differential equations. At the beginning, the emphasis, even if Plenary work was on the holomorphic second-order differential equations, the emphasis was on real differentiable foliations. So in the late 70s and early 80s, 4 groups of mathematicians based on Russia, France, Brazil, and Mexico start to study these holomorphic foliations, and they had quite a few different motivations. One of them, by the motivation of the Russian school, was the study of Hilbert's 16th problem, which is about bounding the number of limit cycles of polynomial real vector fields on R2. We had also a lot of influence, I would say that the French school came from singularity theory. René Thon was big promoter of the theory at the time. And also continuation of work of Poincaré and others, Dulac and so on the normal form of vector fields, local normal form. Just to mention a few results, to give some context, that's not the focus of the talk, but I want to point out that there is a rich theory in the rich local theory, and I highlight some important results on that. So there is a topological criteria for the existence of holomorphic first integrals by Mattei Mussou, results on the existence of separatrices by Camacho Sad, analytic classification of saddle nodes by Martinet-Ramis, finiteness of limit cycles by independently Ekad and Diachenko, and also the work of Yorkos and Peris-Marco on realization of reduced singularities with prescribed holonomy. The global theory took a little bit longer to start to be developed, and I think that there are 2 works in the decade of 1990 that started this line of investigation. One of them is Brunella's classification of smooth foliations on compact complex surfaces, and the other is a result of Cerveau and Svinsneto about irreducible components of the space of codimensional foliations on projective spaces. So let me be a little bit more precise about what kind of objects we are going to be dealing today. So most of the talk will be about algebraic foliations. So it will be an object defined on algebraic varieties by means of integrable algebraic distributions. So algebraic variety is just, roughly speaking, a topological space which is locally modeled over zero sets of polynomials. And algebraic distributions in an algebraic family of vector subspaces of tangent spaces of an algebraic variety. So this is an algebraic distribution. An integrable algebraic distribution is when you impose the condition that the vector fields tangent to your distributions are closed under Lie brackets. So here I draw an example of something which is not integrable, because when it's integrable, Frobenius theorem implies that it's locally defined by submersions, like in the first slide. Okay. One nice thing about algebraic foliations is that they somehow can be defined by finite data. And in the concrete case of projective spaces, for codimension 1 foliations, when the distribution has rank 1 less than the dimension of the space, it's defined by polynomial 1 forms with homogeneous coefficients of a certain degree, satisfying this condition, this descent condition, omega r equals 0, where this degree is a measure of the number of tangencies of your foliation with a general line, and this r that's appearing there is just the radial vector field, to say that this object defined on the Cn plus 1 descends to the projective space. So the integrability condition, the involutiveness condition is quite simple in this setting. It's just omega wedge d omega equals 0. And can be written down in certain number of variables. If I just let this homogeneous polynomial be arbitrary with arbitrary coefficients and think of these coefficients as variables, then in degree 0, after killing this linear relation, we get 6 variables and 1 equation. In degree 1, 20 variables and 10 equations. And so degree 2, 44 variables, 35 equations, 3, 84, and 4. And you, of course, have a general formula that's not that complicated, but I just wanted to give an idea of the complexity of this condition of integrability in the space of all homogeneous polynomial forms. Okay? Very good. So a very classical work by, I don't know, this I think probably can be traced back to Jacobi or Darboux, and say that foliations of degree 0 are quite easy to understand. They are just pencil of hyperplanes, degree 0 in codimension 1, of course, and there's not much to them. And then there is this landmark book by Jean-Pierre Jeanloup. He was a student of Grothendieck, and at some point he decided to understand work by Jacobi and Darboux and try to extend them, and he was able to classify foliations of degree 1, codimension 1 foliation of degree 1, and he showed that they come in 2 families. The one that's written there, like A, is that they are defined by a logarithmic 1 form with poles on 3 hyperplanes, and also there is a pencil of quadrics with a double hyperplane as a fiber. Okay. So let me give a little bit more precise on definition. So foliation for me on a projective manifold X will be given by a collection of vector fields. So for every open set, I will have some collection of vector fields that forms what we call a coherent subsheaf of Tx, of tangent sheaf of F, which is integrable, closed under Lie bracket, and without apparent singularities. This means, for a little bit technical, but this means that the co-kernel Tx over Tf is torsion-free. Of course, where this does not happen, we have the singular set of F, and outside of the singular set of F, we have just this usual smooth foliation. And one important object that we can attach to the foliation, a natural object, is the canonical bundle, which is just the bundle of top differential forms along the leaves, of forms of top degree, which will be technically just the dual of the determinant of the tangent bundle. And this is the so-called canonical line bundle. And we expect, since the work of Italian school and more recently the Mori theory, that the degree or the properties, or numerical properties of this line bundle should control the geometry of the foliation. And we have essentially three different regimes. The negative canonical bundle, these are foliations on P3 of degree 0 and 1. We have the trivial canonical bundle, which would be these foliations of degree 2 on P3, and positive canonical bundles, which are foliations on P3 of degree strictly greater than 2. Okay, so our goal today is to review some results on the structure of foliations with numerically trivial canonical bundle, what also known as Calabi foliations. So the first results trace back to Cerveau-Lins Neto and Polishuk. Cerveau-Lins Neto were worried about extending these results of Joan Lulu that I referred before, describing the number of reducible components of the space of foliations on a certain degree. And the work of Polishuk came from another motivation, which is algebraic Poisson geometry. So here, this condition, when talking about foliation on projective spaces, the condition of being calabial or having trivial canonical bundle is just having degree equal to dimension. And the work of Cerveau-Lins Neto that started this history, it's this paper where they prove that the space of foliations of degree 2 come in 6 families. So here is a picture of the generic element on each family made by a contributor or a collaborator called Brent Pin. And they come in different flavors. I don't think I will describe them, but I would like to mention that to have an idea of the complexity, recall that I described the parameter space of these foliations as a fine space with a certain number of variables. And Kuckerman and collaborators, Kuckerman, Weinschenker and collaborators, computed the degree of some of them. And if you look at this E3 component, has a degree greater than 16,000. So even if you want to do these things on computer, this shows that it would not be an easy task. Okay? So to talk about the work of Polishuk, I need to introduce some terminology, where I will need to explain to you what is Poisson structure on a complex manifold. So a Poisson structure, if you want, is a way, you can say that it's a Lie algebra structure on the ring of holomorphic functions. Or if you want, is a way to associate to each holomorphic function derivation, a vector field, which is the Hamiltonian vector field of that structure, of that function. This can be encoded simply by a bivector pi in a section of the second wedge power of Tx, satisfying some integrability condition, which is this bracket of pi with itself equals 0, where the bracket here is the Schouten bracket, which is the unique natural generalization of the Lie bracket from sections of Tx to section to wedge powers of Tx. And this integrability condition can be easier understood by saying that the contraction of one forms with this bivector, which will give vectors, is involutive. So defines a distribution which is involutive, hence integrable, and has a trivial canonical class. So this will give the foliations where the leaves comes with a natural symplectic structure induced by the Poisson structure. And there is a minor technical point that you should not, if you're not a specialist, you should not be worried, is that this subsheaf is not necessarily saturated, so it might have apparent singularities, but it's a minor point. And in a paper published 1 year after Cervoni Net's paper, Polishuk gave a partial classification of Poisson structures on P3, which is a partial result. It's part of the result of Lin's net. So these two communities did not communicate at that time. So, of course, Polishuk did many other things, but he essentially assumed that the singular locus, which has isolated points and a curve in it, assumed that the singular locus was smooth, and got 2 of the 6 families of Cervoni's net. Okay, so the theory starts from these two different points of view, and so we are in the 90s there, right? 96, 97, and by the end of by around 2008, appeared this beautiful paper by Frédéric Touzé, who started looking at these foliations, really emphasizing that he was interested in foliations with trivial canonical class, and he proved that they come in 3 flavors. Either you have a linear foliation or tori, either you have what we call a Riccati foliation, so a variety has a structure of a P1 bundle over some variety Y with trivial canonical class, and the foliation is transverse to the fibers of P1 bundle, or it's just a fibration by varieties, isotrivial fibration by varieties with trivial canonical class. And his result is saying that these are all examples. So I have to mention also that this extends previous results in dimension 3 by Stéphane Drouel, then a student of Beauville. I think he was part of his PhD thesis, but it was only on dimension 3 and proved by different methods. Here I would like to highlight 2 ingredients of Touzé's work. The first is this structure of non-rich, complete manifold with non-negative rich curvature by Tigre and Gromol. And the other is a splitting theorem by myself, Brunella, and Touzé, where we relate the splittings of the tangent bundle and the splittings of the universal covering of the variety in the direction of a conjecture of Beauville. The assumption is that one of the factors here has dimension 1. So what I would like to stress is that Touzé's result is Touzé's paper is a paper on differential geometry. The techniques are differential geometric essentially, metrics and so on. Okay? But these are for smooth foliations, smooth codimension 1 foliations, and together with Franck Loret, Touzé, we extend for codimension 1 foliations on arbitrary projective manifolds. We impose that the singularities of the foliation are not that bad, are what we call canonical singularities. And we conclude we have something very close to Touzé's theorem, except that we are able to phrase it more intrinsically. So essentially what we are going to have is either isotrivial fibration of Calabi manifolds, or your foliation is defined by a Lie action, an action of an abelian Lie algebra of vector fields, commutative vector fields. Okay, so it will be that times a Calabi manifold. And I just want to give some of the flavor, what techniques goes into the theorem. Notice that the previous result by Touzé was for compact Kähler manifolds, methods of differential geometry. Here, the statement is for projective manifolds. We are assuming that our ambient space is algebraic. And the point is that we actually need that because our techniques are algebraic. So there is part of the techniques which are analytic, which takes care of the case when the manifold is not uniruled. In that case, we are able to verify a conjecture of Paternel and prove that the foliation is automatically smooth and reduce the problem to Touzé's classification. So here the technique is based on Buxton, Demaille, Palm, Paternel theorem, and also on a result of Demaille concerning the integrability of one form with coefficients in pseudo-effective line bundles. I don't want to enter in details, but it's essentially analytic. And then from that, we can conclude that the foliation is defined by a closed ratio on one form, and then standard techniques allow us to deduce the result. In the other case, we do two things. If the foliation is uniruled, we study two different objects attached to our foliation. The first is that we take advantage of the fact that if you have an algebraic variety, the space of curves on it will be a countable union of algebraic varieties. In particular, if we have a uniruled manifold, the space of rational curves on it will be a countable union of algebraic varieties. And each of them, because of this condition of canonical line bundle, comes with a natural foliation. So we study this foliation, we study the deformation of rational curves along the foliation to deduce some transverse homogeneity for the foliation. We prove that it's transversally projective. We also do another manipulation that we can do with algebraic objects, is that if you have something, a holomorphic object but algebraic, is defined by finitely many equations. If you have finitely many equations, you have finitely many coefficients. From that, you deduce finitely generated Z algebra that you can reduce mod P. And in characteristic P, you have new operations with vector fields. You can take Pth powers to obtain new vector fields. And from that, we can prove that either the foliation is defined by a closed rational one form, or if not, we bound the nature of the singularities. Putting these two information together, we are able to prove that the foliation is defined by closed rational one forms. Just to give a hint, and here you see, in both situations, we really need algebraicity. Anyway, I have to mention that this result was not optimal, in the sense that's not what you need if you want to understand the foliation from the point of view of the minimal model program. But a while after we published, Stéphane Drouel and in two papers, one by himself and one with former students of him, Wen Hao Wu, extend our result to projective varieties with KLT singularities, which is the natural setting for these things from the point of view of MMP. So we can say that nowadays, we have a very good understanding of this foliation with trivial canonical class on codimension 1. So the foliation has codimension 1. And the question remains, what happens in higher codimension? So some care has to be taken because in higher codimensions, the things are much more subtle. One thing that I realized together with João Pedro dos Santos is that this problem, for instance, of irreducible components of the space of foliations is very hard. So, for instance, if look at an analog problem, which is the problem of studying the subscheme of the space of all subspaces of a given linear algebra. If you look at the subscheme which parameterize the ones which are closer than the Lie bracket, we get a huge number of irreducible components. In the simplest case, where you have rank 2, we have a simple Lie algebra and rank 2 subalgebras, we get that the number of irreducible components of this thing is in bijection with the conjugacy classes of nilpotent elements of G. And as a corollary, we deduce that the number of irreducible components of the space of degree 2 foliations of dimension 2 grows, with trivial canonical bundle, grows exponentially with n. So it is just a word of caution that we must be careful. Of course, here we are not bounding the singularities. The point is that to have some a more clear answer, we have to control the singularities of these foliations, which are not what we are not doing here. But anyway, in the study of this foliation of higher codimension, being considerably harder than codimension 1, we, together with Touzé, back in 2014, I guess, we look at that somehow more restricted problem, not only assuming that the canonical class was trivial, which means the first Chern class of the tangent is 0. We also assume that the second Chern class of the tangent is 0. And we could prove that when X is not uniruled, then F is automatically smooth, and there exists a splitting of the tangent sheaf of X, the tangent bundle of X. So there is an orthogonal foliation, orthogonal holomorphic foliation. And this splitting reflects as a splitting of the universal covering of X. So we can prove that the universal covering of X is a product of an affine space with a projective of another manifold Y. Okay. And we are also somehow able to control the Zariski closure of the leaves. So the second result is saying that the Zariski closure of the general leaf is an abelian variety, and that they organize as a fibration where the foliation in each fiber is a linear foliation. Okay? I will not enter into the details of the proof, but it passes by the studying of representations. It's based on the work of Zuo of representations of fundamental group of projective manifolds in semi-simple groups, on simple groups, but I will not enter into that. Just like to mention that after working on these objects, worried about the structure of foliations, we also turn attention to the Poisson side of the history. And in a recent paper with Stéphane Drouel, Brent Pin, and Frédéric Touzé, we were able to give a version of this Weisstein splitting theorem. So the local theory of Poisson structures is described by this splitting theorem of Weinstein, which says that every single Poisson structure is the product, locally, the product of a symplectic structure and a singular structure. some Poisson vector that vanishes at a point. And this is local. It's very hard to have global versions of that because this decomposition is not unique. There is no canonical way to globalize it. But if we are studying compact Kähler manifolds with a Poisson structure in it, and I happen to have a compact symplectic leaf with finite fundamental group, then we can actually produce this splitting of the Poisson structure of a finite attached covering. After taking a finite attached covering, our Poisson manifold will be a product of a symplectic structure with another Poisson structure, Poisson manifold. Okay? And so this is a global version of it. I have to say that this does not, we couldn't figure out any other setting that this would work. It does not work in the C-infinity category. It does not work if we drop the compactness of the manifold. If it's not Kähler, it does not work. It's this magic of hard theory that makes this thing work. Okay? And more recently, with the same authors, we could extend this previous result with Touzé. Remember that in the result with Touzé, we were in the projective case, and we had this assumption of projectiveness and non-uniruledness, right? Here, we can extend to the uniruled case, and if we have a foliation smooth with a numerically flat tangent bundle, essentially it's the same thing as saying that C1 and C2 is equal to 0, then we can prove that the tangent bundle is Hermitian flat. We prove also the existence of orthogonal foliation, TG. We are able to verify Beauville conjecture in this setting, proving that the universal covering is a product of a finite space times Y. And we can describe the analytic closure of a leaf, showing that it's a finite attached quotient of equivariant compactification of an abelianly grouped GL in such a way that the foliation is essentially restricted to this thing, is essentially linear. Okay? And as a corollary, we can, now restricting again to the projective case, we can classify foliations, regular foliations with trivial canonical class of dimension 2. And either the foliation will be Hermitian flat, or the tangent shift is Hermitian flat, or the X has a finite attached covering that decomposes as a product of a surface with 0 first-hand class and another one. And complex projective manifold. Okay? So to achieve this, we had to revisit the arguments that we did with Touzé, but had to have some new ideas. And the key new ideas is indeed the concept that somehow we have been doing this thing for, I don't know, all these works, most of the works that we mentioned, but we only single it out right now. So we are being, the settings that we have a foliation on a compact Kähler manifold of dimension P, and we say that F is homologically Kähler. If for any Kähler class, seen as an element of H1 omega 1, the image of its p-th power in HP of the canonical bundle is non-zero. Okay, so this is a concept. This, for instance, when you take a subvariety of compact Kähler manifold, you do that, you always get a non-zero class in the canonical, in the HPP of the variety. The variety has dimension P, but the foliation is not automatically. And we conjecture that this homologically Kähler condition should hold for arbitrary regular foliations, non-singular foliations, and we can verify it in dimension 1, codimension 1. C1 TF equals 0 plus codimension of F 2 or 1, C1, C2, Tf equals 0, or determinant of n star f pseudo-effective. So we can verify in a number of situations, and this was essentially the key to introduce, to prove the previous result, because then we can have a variant of this concept weakly, where we instead assume that for all there exists a Kähler class which is non-zero, because then we can do the following. We have this thing. If f admits an invariant subvariety z, such that f restricted to z is weakly cohomologically Kähler, then f is also weakly cohomologically Kähler. And moreover, if f is smooth with C1 Tf equals 0, then we have the equivalence of several concepts. F is weakly cohomologically Kähler, or there exists foliation G given the splitting of the tangent bundle, or F is cohomologically Kähler, strongly cohomologically Kähler. And these two results put together, they prepare the ground for induction on the dimension and essentially constitute the main ingredient for the proof of the previous result that I stated. Okay? And all this gives a lot of applications to Poisson geometry. I don't understand why there's no titles appearing, but anyway. So we have this conjecture. So probably the experts in the audience have realized that all this is much similar to the description of Calabi manifold, compact Kähler Calabi manifolds, right? So this celebrated Beauville-Bogomolov decomposition says that any compact Kähler Calabi manifold is, after a finite étale covering, a product of what they call irreducible holomorphic symplectic, which is the symplectic components, the Calabi-Aws, and tori. You have these three different behaviors. And here, for foliations, what we saw in codimension 1 is that we still have a splitting of the tangent sheaf of the variety, where we do have similar decomposition, but with the point is that the Hermitian flat part is not necessarily algebraic, it's not necessarily corresponding to compact tori, and there is an extra part coming from the fact that the foliation does not fill the space. There is the transverse direction. So what we believe is that you should have splitting theorems for these objects. You should have splitting theorems for Calabi foliations and also to Poisson structures. So this would be one of these conjectures. We have several of them, but one of them for compact Kähler Poisson manifolds, where we suppose that the minimal dimension of symplectic leaf is equal to D. So this means that the rank of this bivector is D. The minimal rank of the bivector is D. Then we conjecture that there exists a holomorphic symplectic manifold of dimension D, and a holomorphic Poisson manifold Z, and a covering map of Y times Z to X. Of course, neither Y nor Z need to be compact, and this map did not to be finite étale covering, but just a covering, étale covering. Okay? And from putting together all these results that I mentioned before, we have that this conjecture is true for all projective manifolds of dimension at least, at most 5. That's what, if it were at least, it would be good, but at most 5. And this gives, that's the evidence that I have. Okay, I still have 4 minutes, but I think I can stop here and open the floor for questions. Thank you.
Thank you very much, George, for this beautiful lecture. So we have a few minutes for questions.
What's the rule of pi 1, the finite fundamental rule?
Oh. So we are talking about. So if you want, this is a result that you can think of as a fiber product of Rib stability theorem and Weinstein theorem. So having the strategy is to do the following. So if I have a compact leaf, we are able to show that this compact leaf, which is something of smaller dimension than the general leaf, is part of a smooth foliation with that dimension. Okay? And then the finiteness of the fundamental group will imply that every leaf of this foliation is compact. And then I can pass to the leaf space, and Y will be the leaf space of this foliation. So it's conceivable that a similar statement holds for if we drop the finiteness of the fundamental group, but then we would need to go to not a finite étale covering, but an infinite étale covering. But we couldn't decide if this was reasonable or not, so they didn't even phrase as a conjecture. But I believe it's true. But then, but we don't have no clue. Here, what we have is finiteness of the fundamental group, give me a fibration, and then I can produce Y, go to the leaf space of it.
Is there any other question or comment? Yes, please.
It is somehow related to what you said, but there is a wonderful generalization of the Rib's stability theorem by Poisson. So that's the thing that you are proposing.
Yeah, but this wonderful result, I agree, is for codimension 1, right? And the assumptions H1 different from 0, or H1 equals 0 instead of pi 1. Here, since we are in higher codimension, here the codimension is arbitrary. I don't know if it's so simple to produce that, right? Because his idea is just in dimension 1, I think you can show that if you have non-trivial holonomy, then you have a non-zero element in H1. I don't think that's true in arbitrary codimension, but.
There is a version where you have to put some extra hypothesis on the H1 with values on the linear.
Exactly, yeah. You could go in that direction, yes, but.
I don't see any raised hands. So just before we thank our speaker again, let me remind you that immediately afterwards we will have the award ceremony for the Congress prizes. And now let's thank George again for this lecture.